Good afternoon, everyone. My name is Jonathon Lumley, and today I will be presenting my final master's presentation on the optimization of a polymer gel dosimeter for clinical environments. My supervisors for this project were Pejman, David, and Mounir. So just a quick overview of my presentation today. I'll start by discussing the appeal of polymer gel dosimetry along with some promising applications and the mechanisms behind the gel. I'll then move on to discuss about the project aims, the methodologies, the results discussions, followed by limitations, recommendations, future studies, and finally conclusions. So for the appeal of polymer gel dosimetry, over the last 25 or so years, there have been significant advancements in conformal radiotherapy. This has led to a sharp increase in conformity for planning tumor volumes, as well as a large increase in complexity of the treatment. Therefore, to ensure that we're still giving accurate patient doses, we have introduced patient-specific quality assurance tests. These tests, basically, what we do is we measure the dose distribution to a phantom, and then we see the agreement that has compared to the treatment planning system. However, these tests are only accurate as the dosimeter which is being used. So with the increase in conformity, there's also been an increase in steeper dose gradients and smaller field sizes, which have been becoming more frequent, and these can be quite challenging for pre-established dosimeters. Especially for small field sizes, the detector size, the density, and the atomic makeup can strongly influence the dosimetric accuracy. If we were to implement polymer gel dosimeters, we could eliminate potential sources of errors contributed to things such as volume averaging, which is what we see in ionization chambers, directional dependencies that we see in TLDs, atomic composition differences and density differences, which we see throughout most dosimeters. But perhaps the most promising aspect of gel dosimetry is that it's inherently 3D. This means it's able to capture a truly 3D dose distribution without making any assumptions, and it can house complete geometric information. Furthermore, we're able to pour the gel into molds, and we can basically shape anthropomorphic shapes with phantoms with realistic contours and increased dosimetric accuracy. So in terms of promising applications, there have been quite a lot of papers looking into stereotactic radiosurgery, and it's been shown that the polymer dose dosimeters have shown good agreement compared to that with treatment planning systems. Furthermore, since there are no metallic components of the gel dosimeters, they are compatible with MRI linacs. A study by Rod have shown that the gels can effectively measure steep dose gradients in the presence of strong magnetic fields. And what I find really interesting is Didine has shown that the gels actually have sufficient temporal resolution as well to perform real-time 3D dosimetry. Along with these applications, there are many more, such as proton therapy, QA tests, NTN testing, and a lot more. So a standard polymer gel dosimeter is made up of a 6% T, T being the total monomer concentration, and 50% C, which is the monomer to cross-linker ratio. These gels typically include things such as water, monomer, cross-linkers, gelatin, and antioxidants. So the water has a dual purpose in the gel. One, it provides tissue equivalency to the gel, and two, it undergoes radiolysis. So this is basically a process where ionizing radiation splits apart the water molecules, and this creates radicals and ions. And it's these radicals which basically act as the fuel source for the gel. So a little animation I've shown here to demonstrate my point. So the main reaction within the gel is polymerization. This is where we've got a single molecule monomer, which ends up undergoing something called free radical polymerization and converts into a polymer of basically many small little monomers. So this occurs, we start off with our radical, which we produce through radiolysis, and that interacts with the monomer, and that basically propagates the radical site onto the monomer. And then as we can see in this figure up here, each time a new monomer interacts with the polymer, the radical propagates and propagates, allowing us to form these large polymer chains. However, these polymers are actually soluble in water, meaning that they will dissolve in water, and thus we induce cross-linkers. So the cross-linkers basically link two polymer chains together, and what this does is it forms a highly structured polymer network, which is not able to dissolve in water anymore. We add gelatin to the gel to improve structural integrity. This allows us to hold all the monomers and polymers in place. This means that we can basically read out any dosimetric information. And finally, we had to add antioxidants, and these are to scavenge molecular oxygen, because oxygen basically inhibits our gel. When the oxygen interacts with the radicals, it forms something called a peroxide radical. And this is a lot more stable than the typical radicals, and it ends up basically making a stable interaction which doesn't go on to further polymerize. Hence, we end up with dead polymer chains. So typically, polymer gels are read out with MRI, but we use CT for this project. And for CT, polymerization actually induces a electron density change, and this is through two ways. So one, the actual volume of the gel does slightly decrease, and two, local expulsion of water when polymer created also leads to the local density change, electron density change, sorry. So in terms of my project aims, I had three aims. One was to chemically optimize a polymer gel with regards to maximizing sensitivity, whilst also acknowledging other dosimetric requirements such as tissue equivalency. From then, I was going to determine the dosimeter's temporal stability and present recommended timeframes for irradiating and imaging. This was to be done whilst maintaining a realistic treatment deadline. Lastly, through my knowledge gained through the thesis, I was to make recommendations to establish a laboratory within the hospital dedicated for making polymer gels. So my gel, the monomer used was something called a 2-acrylamide 2-methanol propane sulfonic acid sodium salt. It is a very large and long name. This was basically done because it's shown to have adequate sensitivity when used in MRI, and it is currently the least toxic monomer for gel dosimeters in the literature. The crosslinker used was methylene bisacrylamide, which is basically the standard crosslinker, the gold standard, and the antioxidant was tetracus hydroxymethylphosphonium chloride, which is also shown to be the gold standard for antioxidants. So to make the gel, we start off by adding our solvents and gelatin. These solvents can include water and a co-solvent. This is left to sit for 5 minutes to bloom, whereafter we add a crosslinker and we heat our gel up to 40 degrees. The heating is done to dissolve the crosslinker and to melt the gelatin faster. After this is done, we stop applying heat and we add our monomer followed by our antioxidant. Then finally, we wrap up our gels and we put them in the fridge. So for irradiating, all gels were individually irradiated in a water bath. We filled the water bath up until the SSD was 90 centimeters to the water level. And we suspended our vials in the middle of the water using a 3D printed PLA mount. That was basically to ensure that we had sufficient photon scattering. So the parameters used were 6 MV energy photons, 600 dose rate, and a 10 by 10 field size. It was also noted that the gel was rotated 180 degrees halfway through irradiation just to ensure a uniform dose distribution. In terms of imaging, there was 2 different CT scanners used. For the chemical optimization section, I used the Siemens CT scanner, and for the temporal stability section, I used a GE CT scanner. All the recommendations were, all the parameters were based on recommendations, which included 142 voltage, a 300 tube current, a 1 second scan time, a 5 millimeter slice thickness, and 4 images were taken per sample to do a image averaging. So for the chemical optimization, it was quickly realized that to best increase sensitivity, the best way was to increase the total monomer concentration. However, this was limited by the BIS solubility, which is the crosslinker. It was found that this chemical was sparsely soluble in water. And thus, to increase the solubility, we determined it was best to add a co-solvent. 5 co-solvents were tested to see which one was best. They included methanol, ethanol, N-propanol, isopropanol, and T-butanol. These were based on a variety of criteria. So I determined solubility using a gravimetric method, whereby I basically took a 3:7 ratio of co-solvent to water, and I added enough BIS to saturate the solution. I left it there for 1 hour, so basically any BIS that could dissolve in the solution would dissolve, and any leftover would remain solid. So after that, a couple of hours was up, I basically filtered the solution out to leave any of the undissolved BIS behind. I then poured it into a tiny weighing glass and I weighed out the solution, which included the solvent and the BIS. Then I left it dry in an oven to completely remove any liquid, leaving only the BIS remaining, and the solubility could be calculated using equation 1. After we determined which co-solvent was most effective, I then determined what ratio of co-solvent to water was best. So I did the exact same gravimetric method for a variety of different ratios. and determine the solubility. With the solubility known, I could then calculate the optimal amount of cross-linker, monomer, and solvent to be added to each gel formulation using equations 2, 3, and 4 respectively. Each different ratio, 2 samples are made, and they were irradiated at 10 grays and 1 gray to simulate high and low dose regions respectively. Furthermore, to determine if the co-solvent had any negative or any effects on the gel response, I repeated the exact same experiment, but this time I kept the total monomer concentration the exact same throughout all the different ratios, basically just to ensure that the only dependent variable was the co-solvent ratio. And then finally, after I finished chemical optimization, I wanted to determine if optimizing had any effects on tissue equivalency. So I theoretically calculated the Z effective using equation 5 and electron density using equation 6, along with density determined through equation 7. So in terms of temporal stability, I made 5 gel batches for post-manufacture stability investigations. And these were basically all made at different time points and then irradiated at the same time and imaged at the same time. For post-irradiation stability investigations, I made all my batches within a certain time interval, and then I irradiated them at different times and then imaged them all at once. I gave them a variation of different doses, basically to create a dose response curve, and then I apply second-degree polynomial fits and linear fits to this curve. The temporal stability was determined from the variation sensitivity, which was derived from the slope of the linear fit. So in terms of results, N-propanol was determined to be the most effective co-solvent. This indicated that the molecule had an optimal amounts of polar and non-polar functional groups. So the polar groups are from the OH bond, and what they do is they basically bond to the water, whilst the non-polar hydrocarbon groups, which we can see in this chain line here, what they do is they lodge themselves into the polymer matrix, so into the water matrix, sorry, and they basically disrupt any hydrogen bonding between nearby water molecules. This basically lowers down the surface tension of the water and allows molecules such as B.Sc to more actively disperse throughout them, increasing solubility. However, and furthermore, when I tested N-propanol, the B.Sc solubility was approximately 7% weight to weight. This was a 170% increase when just comparing the solubility to pure water. It is noted, however, if I used isopropanol as opposed to N-propanol, we did observe a 20% decrease in B.Sc solubility. This is likely due to steric hindrance effect of the OH group by these C3H groups. So what this happens is that these groups partially shield the OH group and lower its accessibility to form bonds with water. And this basically makes it less energetically favorable to do so. So it is a quite significant effect, as we can see, going from N-propanol to isopropanol to T-butanol. Once afterwards, we looked at the ratios, and it was determined that increasing the amount of N-propanol to water ratio basically significantly increased the solubility of the BIS. So the higher solubility meant that we could add greater amounts of cross-linker into our solution and even greater amounts of monomer, increasing the total monomer concentration. Furthermore, it is noted that when we looked at the BIS solubility in water, it was about 2.6% weight to weight. And this was comparable to other studies which showed around 2.5 to 3%, basically validating the gravimetric method that we used. When looking at the irradiations, it was observed that sample 4 was the optimal formulation. This formulation was then given the name Passage N, and it was shown that the formulation exhibited 163 and 250% increases in HU change for high and low dose regions respectively. This was relative to sample 1. So typically for these higher dose regions, what occurs is that we've often got monomer depletion. So basically there's not enough monomer to continue polymerization and get the large HU change. However, since we have increased the monomer concentration, we've increased the amount of monomers that are available in these higher dose regions, which is why we see such significant changes in HU. As for the lower dose regions, there were always sufficient amounts of monomer, irrespective of what sample was used. However, when you increase monomer concentration, you also increase polymerization rates. So a higher rate means that for the same irradiation, more polymers can be formed, and hence we get a larger change in HU. That being said, though, despite a 14.4% increase in %T from sample 4 to 5, and almost up to 10% decrease in HU was observed. This is due to a direct negative effect from the isopropanol addition. This effect was deemed to be significant at percentages larger than 20% and is likely due to two different effects. So one, enough N-propanol likely acted as a chain transfer agent. This is where instead of the water radical interacting with the monomer, instead it interacts with the N-propanol, resulting in a more stable radical, which is less likely to propagate on with polymerization. Other effect is polymer swelling, where similar to how we increased the bis solubility, addition of propanol allowed for a more friendly solvent, to speak, to basically penetrate into the polymer matrix. This allowed the polymer to swell and increase its volume, which partially reversed the local expulsion of water, which we see through polymerization. In terms of tissue equivalency tests, the mass density of our gel was determined to be approximately 1.04 grams per milliliter. And it was observed in this figure over here in the top right, that no equivalency parameter was more than 5% different at 6 MV. So this suggests that our gel was still equivalent to water, soft tissue, brain, and muscle. It is noted that there's an exceptionally similarity between brain and our passage N formula, which suggests that it would provide a very good dosimetric accuracy when being used for SRS PSQA. It was actually found that chemical optimization actually improved soft tissue equivalency. So if we see our bottom table over here, typically for standard dosimeters, there's often a surplus of oxygen and a deficit of carbon relative to soft tissue. This often requires for publishers to approximate and say that the carbon cross-section is the exact same as oxygen cross-section in order to justify tissue equivalency. How about with our formulation, the introduction of N-propanol and a higher total monomer concentration allowed for the stabilization. And as we see, the chemical composition is pretty much almost identical apart from sulfur. So looking into temporal stability, we see that the linear fit was a good fit from 3 to 48 hours post-manufacture, as well as if we extended the dose region from 0 to 0.5 to 15 grays, we see that polynomial fit is a good fit for all samples. This was because we observed a slight saturation from 12 to 15 grays. It is noted that the 120-hour sample, which was in the purple line here, it did start to display significant amounts of saturation. This suggests that potentially a large amount of auto polymerization did occur, and it is speculated this is due to BIS being sensitive to light. So in terms of the sensitivity differences, approximate stability was achieved between 3 and 48 hours post manufacture with only a 3.9% difference in sensitivity. The stability could be further increased if we irradiate within 24 to 48 hours post manufacture with only a 0.2% difference in sensitivity. Thereafter, it did slightly decrease and became a lot less stable. Thus, we recommend that we irradiate the gel within 48 hours post manufacture. In terms of the y-intercept, there was a significantly large variation, and this is due to an ongoing gelatination process. This occurs in all gel dosimeters with gelatin and can last for about 30 days. So this can be eliminated if we introduce a chemical stabilizer, such as sodium azide. However, this chemical can be quite toxic. Alternatively, we can theoretically apply a background correction whereby we image a irradiated gel with a non-irradiated gel, and that should theoretically allow us to subtract any gelatination differences. In terms of post-irradiation stability, the linear fit saw good fits from samples imaged 1 to 48 hours post-irradiation, and again, the same good fit for polynomial regression was applied for samples 1 to 48 hours post-irradiation. It is noted that the sample imaged 252 hours post-irradiation did not show a good fit for either linear and polynomial responses, with a large variation between the experimental value and the value predicted by the fit. In terms of the sensitivity for post-irradiation, there was a 30% increase in sensitivity when we imaged 1 to 22 hours post-irradiation. However, this significantly stabilized to only a 0.57% variation imaging 22 to 48 hours post-irradiation. As such, we recommend that you wait between 1 and 2 days post-irradiation before imaging. Again, significantly large variations in intercept and y-intercept were observed, which suggests that we should apply background correction to minimize the effects. In terms of comparing to other AMPS-based gel dosimeters, so the post-irradiation stability was very similar to that compared to a gel called PAMSCAT, whereby we saw a rapid increase within the first day, followed by a gradual reduction, whilst a different passage-based gel saw only an increase in sensitivity from 1 hour to 30 days. It is noted, however, that both these gels were imaged using MRI. So in terms of comparing to other gels again, if we irradiate our gel, so if we image our gel within the recommended time frame, we got a sensitivity result of up to 1.056 HUs per gray. And this was approximately 1.2 to 2.6 times higher than any other previously published gel dosimeter that was X-rated CT imaging. This basically shows how valuable it is to optimize gel dosimeters regards sensitivity and to image with recommended timeframes. In terms of the limitations of my experiment, so the post-irradiation tests, they were not all made at the same time and did not all have the same post-manufacture irradiation values. So they were made within 8 to 16 hours post-irradiation, and this is because we could only CT image our gels at one time due to limited availability. In terms of equivalency testing, all tests were only based on theoretical calculations, and we didn't actually observe, we didn't actually do any tests to compare it to, simulated brain tissue and stuff like that. Furthermore, for all the stability tests, only about 5 data points were acquired, so we haven't got a full stability profile yet. Again, this was due because to do this test, we had to make the gel, irradiate the gel, and image the gel, all which took quite a while to do, and I was limited in doing all 3. Finally, there was no validation of dose obtained from the determined calibration curve, so we were able to make a calibration curve, but we weren't able to test if it accurately predicts dose. In terms of recommendations in future studies, currently right now, the clinical feasibility of the passage and dose formulation is not yet apparent. So it's too early to tell, and there are a lot of more future tests required. This would include substituting the cross-link of this, as this is quite a toxic chemical and is also the main source of the light sensitivity. Furthermore, we need to continue investigations into dosimetric dependencies, such as dose rate dependence, energy dependence, and stuff like that, because they are all different for each type of gel formulation. We need to perform validations on the dose distribution, so conducting gamma analysis and looking at percentage depth doses as well with penumbra measurements. And finally, we need to conduct investigations into optimizing the manufacturing time. So it does take quite a while to make our gel, approximately about 15 minutes to make it, an hour to store it. However, it is potentially possible to batch make the gel with and it could have a long half-life. Lastly, so establishing a miniature laboratory would fast track all this testing, and it is considered justified. However, it would cost approximately $15,000 to purchase the fume hood and all the necessary equipment. Furthermore, this shouldn't be conducted until we've substituted the B.Sc, just to minimize any hazards associated and keep it more of a friendly workplace. In conclusion, we optimized a passage-based gel dosimeter, and it was successful. This was the first time that this dosimeter was ever used for CT. We saw up to 250% increase in delta HU when adding 30% N-propanol to water. And we presented a 18.3% T, 30% C passage and formulation. This consisted of a 54.4% water, 23% N-propanol, 12.8% AMP sodium salt, 5.5% Bis, and 4% gelatin, along with less than 1% THPC, the antioxidant. Optimization was actually shown to improve tissue equivalency, and it's best to irradiate the gel within 2 days, as well as waiting between 1 and 2 days before imaging. If we use these recommended timeframes, the sensitivity of the gel was considerably higher than any other published formulations so far. And finally, it was recommended that we do establish a mandatory laboratory. Finally, a big thank you to everyone who's helped me out this experiment. There were quite a lot of you, and I'm sincerely thankful. So these include Pejman, David, Mounir, Brani, Andrew, Broderick, Marco, Siva, Leslie, Myro, and finally the Charlie's Foundation for Research for my discovery grant. These are my references. Do we have any questions?
Excellent. Thanks, John. That was a fantastic presentation. Brandon, looks like we have a question from you. Yep. Brandon, you might be muted. We can't hear you.
Sorry.
Looks like he's up there.
Sorry, can you hear me?
Yeah, I can hear you.
Sorry, yeah, I thought my microphone didn't work. I just put in the chat. Can you see this being extended into phantoms given the troubles and the risk of oxygen contaminations despite the use of THBC?
Yep, so it would depend on the basically the oxygen permeability of the phantom. So if we're able to create a phantom that would basically be sealed off to oxygen, it might be able to be possible, but again, it would depend on phantom size. If this is to be used clinically, we would have to reduce any of the toxicity chemicals. So getting rid of BIS would be the main one, followed by THBC. And there have been a few studies looking at the removal of both.
That's great.
Any other questions? Maybe I can just jump in if there's no others. I guess this is pretty much just a follow-on of the previous question, but is there, sort of just taking a step back, are there any sort of practicality issues that you can potentially think of in terms of getting this sort of gel dosimeter working in actual clinical practice?
Yeah, definitely. So to make this from start to finish, you have to make the gel, store the gel, make the gel, radiate the gel, and then image it. And it can be quite a lengthy time. So it would really depend on what we're using it for. If we're using it just for a one-time treatment of like a complex planning, then it could be feasible. However, if we want to use it more routine, then we would have to, minimize the time between. So one potential test, which I mentioned again here about the optimizing time, would be if we could basically make the gel without the antioxidant, therefore make it basically with oxygen and make it inhibited to any polymerization reaction, then it might be able to be stored long term. That way, instead of having to make it constantly and then store it, we could just have a big batch of it, which you could then quickly add the antioxidant and heating up 5 minutes, quickly cool it down. Adding stabilizers could also reduce the time required to let the gelatin set, and it could be ready within a few minutes. So that would make it more practical, but again, it depends on what it would be used for.
Great, thanks, John. And Pejman or Machine, if you have a question, feel free to jump in.
Yes, thank you. John, that was really good. It shows how much work you have completed. That's great. I just have one question. So you have used CT for your work.
Yes.
How would do you expect any difference if you used MRI?
Yep, so that is one of the issues with polymer gel dosimetry, is that there are a lot of assumptions made. So typically, a lot of different papers will use MRI and they'll say, oh, same thing for CT. So I cannot confidently say without doing it, but there are a lot of assumptions that have been made. It is noted that if we go back to this one here, so this PAN's Passage-based gel was almost similar to our gel. However, it was based on a 6% T, 50% C ratio. And again, there was a significant difference in the stability. So it really, it could depend, but I can't confidently say without doing the test myself.
Thank you.
Any other questions for John?
Just the last one. Just a general question about the making of the gels. Like, how did you find the process of making the gels? Did you find it like a bit tedious, or did you find it like pretty easy going? So what was sort of your experience with it?
Yeah, so initially it was a bit of a challenge. I haven't done chemistry in quite a while. However, once I got more familiar with the making process, it became pretty easy, honestly. It only took about 10 minutes to make the whole entire gel. So it wasn't too bad. We did Adding the N-propanol in such large quantities did initially become a problem. There were large separations. However, I determined that if you add the gelatin after adding N-propanol, these issues basically minimized.
Sounds good.
Great. I think if there's no other questions, then we can leave it there. Thanks again, John, for the great presentation.
Thank you.